Welcome to ReneEnergy.com on YouTube, the hub for all things renewable energy and sustainability.
In the quiet town of Jülich, nestled in Germany's North Rhine-Westphalia region, a groundbreaking revolution in green hydrogen technology is unfolding. At the renowned Forschungszentrum Jülich, scientists are peering into the very heart of hydrogen electrolyzers using advanced 3D X-ray imaging techniques. What was once invisible to the human eye is now being captured in astonishing detail, thanks to computed tomography or CT scanning. This technology, better known for its role in medical diagnostics, is now being repurposed to give researchers a non-destructive way to visualize and understand the complex inner workings of electrolyzers. And it might just be the key to scaling up green hydrogen production sustainably and efficiently. Electrolyzers are the beating heart of the green hydrogen economy. These devices split water into hydrogen and oxygen using electricity, ideally from renewable sources. Central to this process is the membrane electrode assembly, or MEA, where the actual electrochemical reactions take place. But like any technology pushed to its limits, electrolyzers face durability challenges. Over time, performance drops, efficiency degrades, and materials wear out. Traditionally, identifying these internal issues has required destructive testing, taking apart the unit, examining slices, and trying to reconstruct what happened. This method is not only time-consuming, but also risks missing the dynamic, real-time changes that occur during operation. That's where computed tomography steps in. CT scanning allows researchers to take multiple X-ray images from different angles and digitally reconstruct them into a three-dimensional model. This 3D model reveals the internal structure of the membrane, electrodes, gas diffusion layers, and other critical components without ever opening the device. For Forschungszentrum Jülich, this represents a massive leap forward. By inspecting the electrolyzer's interior while it's still intact, they can detect changes over time, identify weak points, and analyze how gases and liquids move through the system during real operation. The advantages of this approach are profound. For one, it provides unprecedented insight into degradation mechanisms. Researchers can observe where cracks form, how delamination spreads, or where water management becomes inefficient. They can study gas bubble formation, ion channel clogging, or microstructural shifts that affect conductivity. All of these insights feed into better design choices, new materials, and ultimately, more durable electrolyzers. For green hydrogen developers and system integrators, that means longer lifespans, higher performance, and lower costs per kilogram of hydrogen produced. But the value of this technology doesn't stop at diagnostics. It also enables what's known as digital twinning. A digital twin is a virtual replica of a physical device fed with real-world data. With 3D imaging, Jülich scientists can create highly accurate digital twins of electrolyzers. These virtual models allow engineers to simulate different operating conditions, predict failures before they happen, and test new design iterations, all without building a single prototype. The ability to model behavior based on precise structural data is a game-changer for green hydrogen R&D. Forschungszentrum Jülich is not working in isolation. This kind of advanced imaging requires specialized equipment and cross-disciplinary expertise. The center collaborates with major academic institutions and industrial partners across Europe and beyond. It houses state-of-the-art facilities like the Ernst Ruska Center for High-Resolution Electron Microscopy and the Saphir Atmospheric Simulation Chamber. Within its energy research division, specifically the Institute of Energy and Climate Research, IEK, the focus is sharply tuned to developing sustainable, scalable energy systems, including hydrogen, fuel cells, and novel energy storage methods. Jülich's approach is uniquely holistic. Instead of treating the electrolyzer as a black box, they are dissecting its function from the atomic to the system level. From catalyst layer optimization to full-stack simulation under dynamic load conditions, the goal is to build a complete, science-backed roadmap toward reliable hydrogen infrastructure. Their CT imaging research fits into this broader mission, supporting everything from materials discovery to predictive maintenance frameworks. What makes Jülich's work particularly relevant is the global push toward net zero emissions. As countries commit to decarbonizing their energy systems, green hydrogen is gaining traction as a versatile zero-carbon fuel. It can replace fossil fuels in industrial processes, serve as an energy carrier, power fuel cell vehicles, and stabilize grids through seasonal storage. but its widespread adoption hinges on lowering costs, boosting reliability, and ensuring safety, all of which depend on better electrolyzer performance. Technologies like 3D CT imaging directly contribute to that mission by removing the blind spots that have long held back electrochemical innovation. Another compelling dimension of this work is its role in quality control and certification. As electrolyzer manufacturing scales up globally, ensuring consistent quality across thousands of units becomes critical. CT imaging offers a fast, non-invasive way to inspect production batches, catch manufacturing defects, and validate design conformity. In the future, it could become a standard tool in gigafactories producing electrolyzer stacks, much like how X-ray scanning is used in aerospace and semiconductor industries today. Moreover, the data collected from these scans have value beyond engineering. They can feed machine learning algorithms trained to recognize failure patterns, optimize operation schedules, or adjust performance parameters on the fly. Forschungszentrum Jülich is already exploring these intersections of hydrogen science and artificial intelligence, aiming to build self-learning, adaptive hydrogen systems. The combination of imaging, simulation, and AI creates a powerful feedback loop for continuous improvement. For the layperson, it's easy to overlook what makes technologies like this so revolutionary. After all, a CT scan might not sound as exciting as a flying hydrogen drone or a futuristic fuel cell truck. But without breakthroughs like these, quiet, detailed, methodical, those big-picture innovations wouldn't be possible. Understanding what happens inside an electrolyzer is like understanding what happens inside the human body. We need clear images, constant monitoring, and deep analysis to ensure the system works efficiently and survives the test of time. Looking forward, this kind of research could pave the way for broader applications beyond PEM electrolyzers. Alkaline and solid oxide electrolyzers, hydrogen fuel cells, even CO2 electrolysis systems for e-fuels could benefit from similar imaging techniques. The underlying principle, non-destructive insight into electrochemical devices, opens doors across the clean energy spectrum. From diagnosing aging battery cells to optimizing carbon capture membranes, 3D CT imaging has potential far beyond today's scope. For startups and companies working in the hydrogen space, the message is clear. Collaboration with institutions like Forschungszentrum Jülich can offer access to advanced capabilities that accelerate time to market. Integrating insights from CT imaging into your design cycle can reduce prototyping costs, prevent field failures, and build confidence with investors and regulators alike. The ability to show a real 3D scan of your electrolyzer in action, backed by peer-reviewed science, can be a differentiator in a competitive, fast-moving sector. For policymakers and funding agencies, this research underscores the importance of investing in foundational tools and infrastructure. Innovation in clean tech doesn't just come from shiny hardware. It comes from deep diagnostics, smarter design loops, and systems thinking. Funding imaging labs, data platforms, and scientific collaborations is just as crucial as subsidizing hydrogen fueling stations or electrolyzer installations. As for the team at Forschungszentrum Jülich, their work exemplifies what's possible when scientific rigor meets global urgency. In a world increasingly defined by climate goals and energy transformation, their ability to look inside the core of hydrogen technology could well define the pace at which this revolution unfolds. The more we see, the more we can improve, and the faster we can build a clean energy future. So the next time someone talks about hydrogen innovation, don't just think about new vehicles or megawatt-scale electrolyzers. Think about the tools that make those innovations possible. Think about 3D CT scanners in a German lab, capturing silent stories inside a fuel cell membrane. That's where the real breakthroughs are happening, quietly, persistently, and with the clarity of X-ray vision.
Thanks for tuning into the ReneEnergy.com YouTube channel. We trust you found this episode and